test. This is a test. This is a
The Double Asteroid Redirection Test. For this global protection run-through, the DART spacecraft developed by Johns Hopkins Applied Physics Lab will fly to the binary asteroid system Didymos, formerly Puff Didymos.
Can't stop, won't stop.
Once there, DART will fly directly into and impact the smaller Dimorphos asteroid orbiting Didymos. Fortunately, the binary asteroid system is not on a collision course with Earth. DART's brilliantly calculated impact of the asteroid will slow its orbit by several minutes without affecting the course of its bigger twin. The twins may actually become closer. A relational, astronomical, and planetary defense win-win. This test has been sponsored by NASA's Planetary Defense Office, aka the Earth Defense Force. Had this been a real emergency, we would have rewatched Armageddon. Welcome to NASA Edge.
An inside and outside look at all things NASA.
We're here at Vandenberg Space Force Base just hours ahead of the DART launch. And Franklin, we've got guests, we've got Launch Services Program Office, we've got a planetary defense mission. How cool is that?
It's very cool, and the way I look at this mission is kind of bringing together the sci-fi movie watching of my youth together with the reality of working at NASA. They're colliding today.
So I gotta ask you, what's your favorite asteroid disaster movie?
I think it's a toss-up between Deep Impact and Armageddon.
Good choices. I went with a childhood favorite, Star Blazers, where the asteroids were pummeling the planet. Of course, those were sent by the Gamelon Empire, so I'm not sure if that really totally applies.
Not really, but we'll go with it.
Okay, well, I tell you what, we do have an interesting office pool today, Franklin. We're going to be asking all the guests, if we can. But we know DART is supposed to slow down Dimorphos by its orbit by an order of minutes, right? So over under 9 minutes. What's your guess?
I'm going to go with the under.
All right, you fairly confident about this?
It's just a hunch.
Okay, awesome. Well, I'll tell you what, let's take a look at the rocket out on the pad. And when we come back, we're going to have our first guest, Dr. Thomas Zurbuchen. And if he's up for it, we'll get his take as well. Joining us now is Dr. Thomas Zurbuchen, Associate Administrator. Thomas, thanks for being on the show.
I'm so glad to be here always.
This is such an exciting mission. I mean, we don't often talk about planetary defense, but here we are. So I'm wondering, how does this kind of mission fit into NASA's overall mission?
You know, we do a lot of science in many different ways. And we're lucky when the science we do helps protect lives on Earth. And of course, our climate programs, dealing with the climate crisis, but our space weather and low Earth orbit safety programs are that. And planetary defense is the third such domain. And it's the first mission in this third domain. More missions to come as we go forward.
Okay, well, that's a great segue into my next question, because I'm thinking it's really important that we demonstrate this capability, but also we need to develop it moving forward. How will that play into future NASA missions?
You know, the most important priority beyond this tool now, which is the first mission, is really to find all the threats. At 140 meters of and up, you know, kind of football stadium size. Those are kind of city scale kind of challenges. So let's go find them all. We've only found 40% so far, we think, based on our models. So let's go find the others. That requires ground-based observations, it requires a new mission. And then for me, what really is important after we have the tool is to figure out how we, you know, now advance this technology going forward, perhaps create other technologies that help mitigate such impacts.
Right, so not just impacting and sort of shifting orbits, but maybe something more developed.
Exactly right. So for me, it's like, so there's a number of ideas people could have, right? Kind of, and technologies that are developed. And it really depends on the orbit, the size, and also the advanced warning, right? Kind of, if, frankly, kind of a multi-mile asteroid is inbound, really surprisingly, really quickly, there's very little we can do. But the good news is there is not such a thing. We found from 1 kilometer and up, we think most of the asteroid.
And that's reassuring. And of course, in this mission in particular, this asteroid system is not on a collision course, so it's the perfect test bed, if you will.
Exactly right. In fact, not only is this not on the collision course, we don't know of one on collision course in the next 100 years. So this is the right time to do this work.
Awesome. So one question, this is particularly important because of our NASA partnerships. Johns Hopkins Applied Physics Lab put together a great spacecraft. How important are these partnerships moving forward with planetary defense?
Exploration, whether it's robotic or human exploration, is a team sport. And partnerships both with our commercial partners, often cross-agency partners. Also here, we have FEMA involved and international partners is absolutely critical. Global challenges require global partnerships, and that's what happens in all of these domains I mentioned.
Awesome. Well, I've got one final question before you go. We're doing an office pool. As you know, DART will slow Dimorphos's atmosphere orbit down on the order of minutes. So with 9 minutes being the standard, would you take the over or would you take the under?
I'll take the over. I think it's going to be, if Dimorphos is really a gravel pit, like we think, you know, like Bennu was, there's going to be a lot of stuff coming off. So I'll take the over.
Okay, so Dr. Z takes the over. Okay, this is good, because in a year we'll have the results and we'll be able to see how well we're doing.
I hope I'm right by that time. I look forward to that interview.
Well, okay, so did you do calculations? Or is that just based on your gut feeling on the mission?
You know, I'm a physicist by training, so I sit down. I was trying to figure out kind of what is that beta parameter everybody's talking about, and you know, like how much would it take? And it's like, well, that, you know, considering what we saw from Bennu and this kind of, it's possible. Of course, I don't know is the short answer. That's why we're doing the experiment.
That's right.
But I don't have any magic somewhere. I'm certainly not a specialist in this. But yes, I did sit down and just try to figure out, like, well, how much would it take? So I thought it's realistic. And frankly, our teams tell us, look, it may be 10 minutes, it may be more. So there you go.
Awesome. Well, thanks so much for being on the show. We'll see how you do against Franklin and others in about a year.
All right.
Up next, Franklin had a chance earlier this week to sit down and talk with NASA's Planetary Defense Officer.
Right now, I'm joined by Lindley Johnson, NASA's Planetary Defense Officer. How you doing today, Lindley?
Good, Franklin. Glad to be here.
So tell me, what do you do at NASA in the Planetary Defense Office?
Well, I oversee, with my team, all the projects that NASA is involved with to look for asteroids in space, determine if any of them are a hazard to impacting the Earth, and then working with U.S. government agencies and our international collaborators, agencies around the world, to figure out what we would do about that if we had an asteroid on an impact with the Earth.
Back in, I think it was 2014, we had the Planetary Defense Conference in Flagstaff, Arizona, and the NASA Edge team was there. We were doing a show. Everybody should actually go back and look at those shows.
A good conference.
Yes, it was a great conference. Some of these things were being discussed then, and now you actually have a mission.
Here we are, yes. Yeah, we were talking about this kinetic impact concept back in those years. Developing the advocacy to get the funding and the approval to do this mission, which we formally started this mission in 2017. So we've been about four and a half years getting here.
Tell us, how does the Planetary Defense Office locate near-Earth objects?
Well, we have a group of ground-based observatories that we sponsor that are searching the skies every night to try to find these asteroids. We found some 27,000 now near-Earth asteroids of all sizes, of which about 10,000 of them are large enough that they could really do serious damage if they were to impact the Earth. None of the ones that we've found so far are a significant hazard to the Earth, but we know we've only found about 40% of what we believe is out there.
Our viewing audience will say, you know what, we haven't had any significant near-Earth object
Impact. Yeah.
impacts, but they have seen like the asteroid that came through Russia.
Right,
Now,
yeah.
How does that asteroid compare to what we're searching for and what we want to intercept?
Well, in fact, you can go out every clear night and see small rocks impacting the Earth, what we call meteoroids impacting the Earth. That's the small end of the scale. Asteroids are just bigger rocks that, if they're large enough, could penetrate Earth's atmosphere, cause at least an air burst at the surface, a blast wave, actually a crater with the ejectile. The event that you're referring to was in 2013, Chelyabinsk, Russia. That was an asteroid about 17, 18 meters in size, 60 feet in size, that entered Earth's atmosphere over Russia, caused quite a bit of damage, some $30 million of damage, and injured 1,600 people because of the windows that it broke in on them as they were standing there watching the light show.
If we actually had to intercept an asteroid, how far out do we do something like that?
As far out as we can do it. That's the whole strategy of our planetary defense program, is we are looking for these objects far out in space. And we can find them years, decades before they're really a hazard to the Earth. We have the technology to do that. So we find them, track them, determine what their orbits are, and then we project those orbits into the future. And we can project, pretty confidently as much as a century into the future. And then if they're large enough, Earth's atmosphere won't take care of it for us, then we've got the time to do something like DART to deflect that asteroid off the offending trajectory.
We know Didymos has its moonlet that is the target of DART.
Right, yeah, Dimorphos. Mhm.
Yes, but DART also has a companion spacecraft. Can you tell us a little bit about that?
Oh, that's right. Yes, the Italian Space Agency has contributed a CubeSat to ride along with DART. We're deploying Lucia Cube about 10 days before the impact. That CubeSat will follow us in and image DART as it impacts Dimorphos. We'll get an idea of the ejecta cloud, how much material is being blown off the surface. And also, hopefully, it'll be able to image the rest of the asteroid, because DART will never see the backside of Dimorphos or the backside of Didymos, for that matter. And so it'll contribute a lot of additional data that the scientists can use to fully analyze the mission.
Lindley Johnson, NASA's Planetary Defense Officer, thanks for being on the show today.
Yeah, I enjoyed talking with you, Franklin.
As Mr. Johnson exits, our next guest will be walking on here shortly. With the crazy schedules this week, we had to kind of corral everybody and bring them on the set at the same time. So that's why we're doing it this way. And right now, I'm going to introduce Mr. Andy Rifkin, who is NASA's DART investigative lead. How you doing today, sir?
Great, Franklin. Thanks for having me.
Exactly what do you do as an investigative team lead for DART?
So, like any mission, DART needs to do certain things to be considered a success. My job is to make sure that the data we take, particularly the data from the ground-based telescopes after DART's impact, answers the questions that we need to have answered, and to make sure that these analyses get done to the precision that they are required to get done.
Now, is it just the ground-based telescopes, or do you deal with any of the data that will come from the satellite itself?
I'll help deal with some of the data from the satellite as it's coming in. It's going to take images of the surface of Dimorphos. We need to look at the geology of Dimorphos. We need to see if we hit a giant rock or more of a flat piece. So I'll be helping out with that piece, but most of my focus is on the ground-based telescopes and any space-based telescopes we get data from.
Now, can you tell me why we're going to this Didymos system rather than hitting just a asteroid that, will orbit around Earth and the Sun?
Absolutely. It's a great question. Asteroids and the Earth, actually, both move around the Sun at something like 20 miles a second. We think that we only want to give a little shove to asteroids when we deflect them. We don't want to push them too hard or they'll just come apart, and that's not what we want. So we want to change the speed by maybe an inch per second, maybe even less. Measuring the change of an inch per second or less on a a 20 or 30 mile per second speed around the sun is very hard if you don't have a second spacecraft. The moonlets only move around their parent asteroids maybe 6 inches a second, maybe 7 inches a second. So we can change the orbit by just a fraction of an inch per second and make that measurement very easily from the Earth. The second part of that, and another reason why that's true, is because Dimorphos moves in front of and behind Didymos from the point of view of Earth. So we can watch the brightness of the system, see the brightness go up and down, and by measuring how often that brightness goes up and down, we can measure the orbit period of Dimorphos. We've been measuring it for a while. We'll measure it again after we hit, and we'll compare the results, and that's how we get the answer we're looking for.
And the information you get from that will tell you exactly what, if you were to transfer that to an asteroid that, could possibly impact Earth.
We think that most asteroids are rubble piles, as we call them. They're not solid rock the whole way through, but we don't actually know. When we crash a spacecraft into an asteroid in a kinetic impactor test, like DART, some of the momentum or all of the momentum will go into the asteroid. We might make debris, and that debris also carries its own momentum. Depending on the amount of debris that's made, how fast that debris is going, it could give the asteroid an extra push in addition to what the spacecraft itself is doing. So we need to know, is that a big push? Is it a little push? Can we count on that kind of effect or not? If this is going to need to be used for real, we'll want to understand very well what kind of effects we can expect.
Andy, this is some very interesting things. I'm looking forward to the data that we will receive from your ground-based telescopes down the road here. Thanks again for being on the show.
Pleasure. Thanks for having me, Franklin.
Back to you, Blair.
Joining us now is Lori Glaze. And Lori, thanks so much for joining the show today.
It's my pleasure.
Well, listen, I want to talk about DART's navigation. I understand it has a very complex navigational instrument. Can you tell us a bit about Draco?
Yeah, let me tell you about Draco.
Or Draco,
So,
sorry.
yeah,
I
the
see it
Draco instrument. I think it probably could be either way. So what's really cool about the DART mission is it only has one instrument, and it's Draco. And Draco is essentially the eye of the DART spacecraft. It's a narrow-angle camera that will take extremely high-precision images as we start to approach Didymos and Dimorphos, and as we get really close to Dimorphos, like I say, these very high-resolution images, and then they're going to be processed on board very rapidly, and the image data will feed into the navigation system, something the software called SmartNav, that will then feed information to the spacecraft so that it can navigate and adjust as it starts to get close to Dimorphos, so that when we come in at 15,000 miles an hour, traveling 4 miles in the last second, that we're targeting exactly where we want to hit.
And that's really impressive, because when you're moving at those speeds, sending those images and being able to make those decisions is really critical. Now, what kind of margin of error do we have? I mean, does it have to hit at the exact spot, or does it have a little bit of latitude that it can hit?
That's a really, really good question. And in fact, we believe that has a fair bit of latitude. We don't actually know the shape of Dimorphos. We don't know if we're going to get a head-on impact or a slightly glancing blow. But we believe that even a glancing blow is going to have some impact that we'll be able to measure, have an influence we can measure. But in the best case, we want to hit it dead on.
So you're going to put a little English on it.
Yeah, a little English, yeah.
All right, well, listen, I also understand that this imager is based on technology that we used in a previous mission, New Horizons, the LORRI instrument.
In fact, yes.
the LORRI instrument.
Yeah.
Tell us about that.
Yeah, so you're absolutely right. Draco builds on the past heritage of the LORRI instrument, currently flying on New Horizons. The LORRI instrument, of course, is the high-resolution imager that took those beautiful images of Pluto.
Yeah.
Just absolutely spectacular images of Pluto. But we're building on that technology. That's an instrument built by Johns Hopkins University Applied Physics Laboratory. And the new version, Draco, is a new evolution where we now have improved detectors that have lower noise, so more signal to noise, so higher quality images, and a new optical system that's higher spatial resolution. So just a really incredible camera.
Real quick, will those images that it takes for navigation be sent back as well?
So there will be some images sent back until we impact, because once we impact, nothing else comes back. But keep in mind that all of that processing and the decision making is all done autonomously on board. There's no time to send images back to Earth and us make decisions and send them back.
Sure.
So all of that is done on board.
Awesome. Well, one final question. We're doing an office pool on how slow we will affect the orbit of Dimorphos. So with 9 minutes being the standard, will you take the over or the under?
Oh gosh, for me, I'm going to go over. I'm the optimist. I am an optimist. I think that we are going to hit it as dead on as we can, and I'm definitely going over 9 minutes.
I see a clear trend among the scientists, for sure. Thanks so much, Lori, for being on the show.
It's my pleasure.
Up next, Franklin has a chance to sit down with one of the DART team members and talk about the spacecraft. Let's check it out.
I'm here with Lisa Wu, part of the DART engineering team. How you doing today, Lisa?
I'm doing great.
Tell me a little bit about what you've done with DART at the APL.
Yeah, so as you said, I am a mechanical engineer at the Johns Hopkins Applied Physics Lab, and I work on DART. So one of my main responsibilities was integration and testing. I was the mechanical engineer in the clean room putting the spacecraft together. I basically helped build DART, which is so cool to say.
Well, you know, you're so excited about this. I have to let everybody know that you're just 4 years out of the University of Maryland. You're working at APL, and this is your first major mission. And you have a lot of responsibility as being part of a very diverse DART team. Tell us a little bit more about that.
Yeah, it's awesome. So about 50% of the people I work with are women, and it is just so cool to have all of these amazing mentors. And everybody on DART is so nice, and it's so cool to be a part of something so big.
Speaking of big, DART is not very, very big, but you were working with DART at APL doing integration testing. Now, sometimes when you have a spacecraft, they're shipped out to do, you know, your vibration tests and such. Not so with DART. Tell us a little bit about what you did with DART at APL.
Sure. So the DART spacecraft was entirely built and tested at the Johns Hopkins Applied Physics Lab, APL for short. So DART is small enough where we could have all of these different components or structure, the solar array, all the little piece part boxes built in-house, and we could just roll it down the hall into our vibration lab and then put it on the table and vibe test it. And then we could also just push it down the hall and put it into our thermal vacuum chamber to do TVAC testing. So that was also really cool. And we're small enough that we could fit in all of these facilities. And APL is awesome that we have all of these facilities that we could build and test the spacecraft there.
Now, as part of your mechanical engineering or your engineering duties, you had to work with the logistics of getting a DART from Maryland out here to California. Tell us a little bit about that.
So, yes, that was a really long road trip, as you can imagine, coast to coast. Our drivers, our folks from our shipping, they were amazing, and we all worked together. We did so many practice runs, because you can imagine we are shipping this very expensive spacecraft across the country. We want to do as much practice as we can. We had a specially designed shipping container for our spacecraft, and through everyone's hard work, we were able to ship the spacecraft in roughly 2 days. Nonstop driving, oof. What an adventure.
So I understand you've been here for quite a while.
Yes.
Tell me a little bit about that.
Of course. So once we ship the spacecraft across the country, we need somebody over here to actually receive it and take it out of its shipping container, get it set up for its last-minute finishing touches before we can actually put it onto the rocket. So that's what I've been doing out here, finishing touches, putting it on the rocket, and just being here for launch.
Now, the container that DART was shipped in is right in the hangar that we're in, and I understand you had to come and embrace the container when you walked into the hangar.
I was very excited. This container basically was the safe haven for our spacecraft, the spacecraft that I've been working on for the past couple years. So, of course, I was very happy to see it. It's in one piece, the spacecraft's in one piece. Yeah, the container did its job very well.
Good deal. Well, Lisa, I'm happy to have you on our show today, and good luck with DART. We'll hope to see some good positive data from this mission going forward.
Great, thank you so much.
Joining us now is Launch Services Program Office's very own Mick Woltman. Thanks for being on the show today, Mick.
Appreciate it, Blair. Glad to be here. Excited about the DART mission.
Yeah, me too. And this is always an exciting part of the show for me because we get to find out what's going on with the rocket, which is, you know, one of the coolest parts of
Yes.
any launch, right?
We in Launch Services Program love the rocket. We love our science missions. But yeah, we're passionate about the rocket work.
So my first question, though, I want to talk to you because the rocket rolled out overnight, and then it rolls out horizontally, but it does something a little different. Then it goes vertical. So tell me about this process that SpaceX uses. It's a little bit different than what we've seen in the past.
Yes, so roll out of the SpaceX Falcon 9, you're absolutely, it comes out of the hangar horizontally. The team gets it out to here at Vandenberg, Space Launch Complex 4, and they prep it, getting it ready to go vertical. But prior to that, they'll hook up all the quick disconnects. They'll power up the vehicle, test it out, make sure everything is working prior to going vertical, which they did later or earlier this morning.
Right.
And then once they go vertical, they are now ready for launch, getting into their terminal count. Because once it's vertical, it's very hard to access because of the erector trailer that they've rolled out on. They used the same trailer they rolled with to bring it vertical on the pad.
So in that case, though, say there was a problem, not suggesting there would be, but if they have to go back, once they've gone vertical, you know, they have to launch, or could they, in a certain circumstance, actually go back?
Yeah, there are contingencies if they had to get out to it, the man lift or something like that. But typically, that's why they do all the checkout prior to going vertical.
Okay.
Once they go vertical, they are ready for launch, getting into that terminal count. You know, in all the missions that SpaceX has had, they have perfected this roll to the pad, checking out, and then going vertical. They haven't had to do that. So, but there are contingencies out there if it needs to be.
Awesome, but so far so good, right?
So far so good. It's going great. The teams, both SpaceX, NASA LSP, and the spacecraft team has performed very well, gotten through all our reviews, all of our testing, and we're just kind of in what we call crew rest right now, getting ready to come on console later this evening, getting ready for launch tonight.
Well, I'm wondering, earlier in the week when I first saw you here at Vandenberg Space Force Base, you were doing or monitoring a static test?
Yep, static fire.
Static fire. I was like, what testing are they doing? What's going on?
So that's actually a unique test that SpaceX does. It tests out the ground and control systems of the rocket. You can think of it as kind of a wet dress rehearsal, right? We tank the vehicle, we detank the vehicle, but as part of that test also, SpaceX does a 7-second static fire. They actually light the engines and test out all the turbines on all 9 engines, make sure everything's working properly. That's a unique thing with this vehicle, again, because of the reusability. So, interesting fact for DART, this is NASA LSP's first previously flown booster. We actually used this booster, Booster 1063, on the Sentinel-6 Mike Freilich mission back in November of 2020.
So like a year ago?
Yep, a year ago. And in that time, SpaceX then took the booster, shipped it to Florida, flew a Starlink mission, recovered it, shipped it back here to Vandenberg for the DART mission. So this will be the 3rd flight of this first stage booster.
I mean, that alone is incredible. But what's the shelf life on reusable rocket? Like, how long can you do this? I know that's great that we do it, but how long?
So yeah, SpaceX has a few boosters out there right now that they've flown at 10 to 11 times.
Wow.
Ultimately, they'd like to get a lot more. We, NASA LSP, continue to work with SpaceX. We look at qualified life of the vehicle and how we can use it in our mission. So like I said, DART is a 3rd flight. Our next mission up, which we hope to see you on the East Coast with, will be IXPE mission. Yep. It will be a previously flown booster also, and we're taking advantage of that reusability of that first stage.
Awesome, great stuff from SpaceX and Launch Services Program Office. But I've got to diverge from topic for just a little bit, because throughout the show we've been asking everyone, the guest, the over/under. As you know, DART is supposed to slow Dimorphos's orbit, and by an order of minutes.
Yep.
So 9 minutes. Would you take the over or the under on whether DART will slow it down?
I'm going to take the over. I have a lot of faith in the science team and the work they've done, and I know the rocket's going to perform well, getting DART on its mission, and so I'm going to take the over on that.
All right. Well, I'm glad you have faith in the system. Thanks so much for being on the show. Really appreciate it.
Thank you, Blair.
You're watching NASA Edge.
An inside and outside look of all things NASA.
Happy Thanksgiving.